All right, welcome, class. I am so excited to be your guide today as we uncover some hidden secrets of the everyday world around us. I mean, look around wherever you're sitting right now. You've got desks, chairs, maybe your computer, maybe there's a gentle breeze outside your window. But what if I told you that everywhere you look, there's this invisible toolkit at work? We're talking about unseen pushes and pulls that literally govern everything we do. In this explainer, we're going to take the invisible and make it totally visible.
Let's just jump right into a mystery I'm sure you've all bumped into at some point. Think about it. Why does a super heavy box finally slide across the floor when you give it a really good push? But a stalled car, yeah, that requires two people pushing together just to get it to barely budge. To solve this today, I need you all to put on your imaginary physics glasses. Go ahead, throw them on. Because once you're wearing them, you are going to start seeing the invisible rules that control how every single thing in our universe moves.
Okay, let's dive into this. At its absolute most fundamental level, a force is, well, it's simply a push or a pull. That's really it, the whole shebang. Just think about kicking a resting soccer ball. You are applying a force to it. Your foot pushes that ball, and that invisible push causes the ball to instantly change its state. It goes from just sitting there chilling on the grass to flying right through the air.
Now here's where it gets kinda wild. Forces do a lot more than just cause motion. They can actually alter the physical shape of an object. Imagine squeezing a fresh lemon. When your fingers apply a force to it, pressing inward, the lemon's shape completely changes as all that juice squishes out. So, with your physics glasses securely on, you can see that forces can start motion, stop it, change a moving object's direction, and even squish and stretch the shapes of things around us.
So here's a crazy fun fact for you. In our everyday life, the absolutely tiniest forces we can directly feel are somewhere in the ballpark of millinewtons. Think of that like a super light touch on your arm. But scientists today, they've got these incredible tools that can measure unimaginably tiny forces down to yoctonewtons. That is 10 to the power of negative 24 newtons. To put that in perspective, that's a decimal point followed by 23 zeros and then a 1. So yeah, even the absolute tiniest interactions in the universe rely on these pushes and pulls.
Now, you definitely just heard me drop the word newtons. When we measure the magnitude, which by the way is just a fancy science word for the strength of a force, we use a standard unit called the newton, and we write it with a capital N. It's named after Isaac Newton, the famous scientist who figured out the 3 laws of motion way back in 1687. Technically, 1 newton is the force that makes a 1 kilogram object accelerate at 1 meter per second squared. Basically, when you push a door open, you are applying a very specific number of newtons of force to get through that door. So, the absolutely crucial point here is figuring out what happens when multiple forces act on an object at the exact same time. And there is no better analogy for this than a classic game of tug of war. If both teams are pulling the rope in opposite directions with the exact same strength, we call those balanced forces. Because the pulls are equal and opposite, it's a dead tie. The rope doesn't budge. But if one team suddenly pulls harder, applying a force with a larger magnitude, well, the forces are no longer balanced. And what happens? The rope jerks in the direction of the stronger pull. Unbalanced forces are what create motion.
Okay, let's take our physics glasses off the grassy field for a second and take a quick trip over to this swimming pool. Water actually introduces a really cool environment for us to examine a bunch of invisible forces acting on an object all at the same time. Just imagine a ball floating peacefully right on the surface of the pool. It looks like absolutely nothing is happening, right? But look through those physics glasses. We are actually looking at a hidden battle of forces. Pulling heavily straight downward is the gravitational force. That's the mass of the Earth acting on the ball. But pushing back strongly upward against it is the buoyant force coming from the liquid water. And because that ball is just bobbing there, not sinking to the bottom, not rocketing up into the sky, those two opposite forces are balancing each other perfectly. But wait, what if the forces aren't fighting each other, like in the tug of war or the floating ball? What if they actually team up? Think back to those two people pushing a stalled car. They're applying force in the exact same direction. When this happens, their forces don't cancel out. They actually add together. Their combined effort creates a much larger net force, and it's this combined net force that finally gives them enough power to make that heavy car roll forward. All right, let's bring it back to dry land so we can finally solve our initial mystery. Remember that heavy box from the beginning of our explainer? The one that was so frustratingly difficult to slide across the floor? Well, let's figure out exactly why that is. Let's break down the invisible toolkit acting on that box right this second. There are actually 4 distinct forces at play here.
First up, there's your applied force. That's literally your hands pushing the box forward. Second, you have the force of friction. That's the rough surface of the floor scraping and pushing back against your push. Third, there's the gravitational force, meaning the weight of the box is pulling it straight down. And fourth, there's what physicists call the normal force, which is simply the solid floor pushing straight back up. And hey, notice how gravity pulling down and the normal force pushing up perfectly balance each other out vertically? That perfect balance is exactly why the box doesn't magically float up to the ceiling or go crashing down through the floorboards.
But what about moving it horizontally, right? Like, why is it so hard to push? Well, the box is only going to slide forward when your applied push becomes stronger than that force of friction pushing back at you. When you finally push hard enough, you break the tie. You create an unbalanced net force in the forward direction. Simply put, if you want motion, you've got to overcome friction.
And this brilliantly illustrates the whole core of what we've been learning today. So, it is time for a quick, interactive final exam. Let's see just how well your new physics vision is really working.
All right, here is your question. If a weightlifter holds a massive, super heavy barbell completely steady over their head, are the forces acting on that barbell balanced or unbalanced? Think about it for a second. Apply what we just learned about the tug of war and that floating pool ball. You got your answer? Well, because the barbell isn't moving at all, it's completely locked in and steady, the upward push from the lifter's strong arms and the downward pull of the Earth's gravity must be perfectly equal, meaning they are perfectly balanced forces.
You all did an absolutely amazing job today. As we've seen, forces really are this invisible toolkit building the motion of our entire universe. We're talking everything from kicking a soccer ball to floating in a pool to pushing a stalled car. So I want you to keep your physics glasses on as you head out today. When you're riding your bike, opening a door, or honestly even just sitting, resting in your chair, ask yourself, what invisible interactions, what unseen pushes and pulls are you going to spot next? I guarantee you they are literally everywhere, just waiting for you to notice them.